and in particular, I've analyzed the radiation pattern both for the single element and for the array of fibers. I've studied a new confinement mechanism for tube lattice fibers, and I considered conditions for single mode operation, such as the excitation with a Gaussian beam, but also a different number of rings around the core and various geometrical dimensions in order to modify the core size. For the lack of time today, I will show you. I will talk you only about the second point. In particular, tube lattice fiber is presented in this slide and has a cladding made of a triangular arrangement of hollow tube waveguides, and the core itself is hollow, so made in air, and this feature allows to reach low losses for the terahertz ranges. Other advantages respect photonic bandgap fibers rely on the fact that they achieve wider transmission bands, and also to the fact that they can be obtained by simple assemblage without any drawing process. The main problem for these fibers is that there is a lack of theoretical models able to describe its spectral behavior for guided modes. And his confinement mechanism is based on the low density of states, and so it's based on the weak coupling, which we code between core and cladding modes, which are represented on the right side. We can find two kinds of situations. The first one, presented on the top of the slide, is when there is no coupling between this kind of solution, and so there are low losses for guided modes, and we have high transmission windows presented here. While on the other side, when we have coupling between two kinds of solution, we have high losses for guided mode. Previous models that have been proposed in literature were only empirical ones, so they were only able to predict the spectral position of the high loss regions, but they were unable to predict their spectral width. So our goal has been to formulate a theoretical model. And our idea is that we can consider the cladding as an assemblement of hollow tube waveguides, so we can study analytically the single tube, then use a couple mode theory to describe mode of the interior cladding. For such a waveguide, there exist a lot of modes, but they can be classified considering their radial and azimuthal dependence, as is shown on the right side. And they combine each other in order to form the cladding mode, as one of these is depicted in the bottom part of the slide. As I told you before, the tube waveguide is well known analytically, and modes can be studied considering a variation of geometrical parameters. For example, here we want to present effect of variation of the rho parameter, which is the ratio between the internal and external radius of the single tube waveguide that compose the cladding. And what we may have seen was that moving from rho values of 1 towards 0, we have frequencies of the modes of the cladding that tend to spread over a wider range. So we will find points of critical values of rho where the transmission bands disappears. This value of rho will depend on the transmission band that we are considering, and in particular they tend to diminish if we move from lower to higher transmission bands. For numerical validation of our model, I'll show you 3 examples with different values of rhos. The first one is a rho value of 0.4. Okay, this was the graph presented in the slide before. And so the first one is the rho value of 0.4. So we have our model and numerical results for losses of the fundamental mode of the microstructured fiber. Here we see that there is no transmission windows in these frequencies that we are considering. So if we move to a higher value of rho, in particular 0.65, we have the clearly second window, while the first one is only slightly sketched. And in the last case, we have both transmission windows. We see in this way that our model is confirmed by numerical analysis. With this, I have concluded. Thank you for your attention, and I'm available for questions.